So today I would like to talk about a very simple sounding and quite naive question. What is a circle? So the reason I think this is worth looking at is that circles pervade so much of our thinking about the world. The idea of these simple geometric shapes which appear all around us in nature and in technology, the idea of repetitious events and objects, the idea of a set of points which are somehow symmetrically spaced around a centre. These notions are really all around us, and so I think it's worth going back to the very simple sorts of questions which a lot of us probably take for granted about circles. The simplest one, I think, being, what are they? Okay, so I also think it's very interesting to see how many different ideas come about once one starts to consider circles. I mean, I don't think it's much of a coincidence that lots of portals to other worlds and such in literature are often circles. I mean, once we start to consider them, we get all kinds of ideas of curvature, cyclic nature, boundaries, irrational numbers, complex numbers. A whole plethora of nonlinear phenomena emerge once one starts to consider circles. I was talking with my friend Joss Huber about what's going on here, and his reply was that a circle is, as he called it, the end of linearity, and I think that's a very good way to put it. Once we start to go beyond the line and into the circle, a whole plethora of non-linear phenomena come about. Okay, so when we think about a circle in terms of numbers and measurements, it's important to consider what types of numbers we're going to allow. For example, if we're only going to allow counting numbers, then we can approach the concept of a circle through that of polygons. Regular polygons, with increasing number of sizes, become more and more like the circle. In fact, this is the concept which led Archimedes to derive an approximation for the value of pi, by approximating the circle by a polygon with more and more sides. Is the circle actually a polygon with a very large number of sides? Well, technically the answer is no, but one can approach that form and therefore learn a lot about the circle. Okay, so there are in fact lots of number systems which we can use to consider a circle. As I said, we can consider integers. We can also consider a circle where all the points have rational coordinates. I shall talk later about how that's done. There's quite a lot of use in that. But of course the normal way to consider a circle is within the real number system, where we don't just include rational numbers, those are essentially fractions, we also include irrational numbers like the square root of 2 and pi, which of course comes from the circle in some sense. But we don't have to stop there. We can use even more rich and exotic mathematical objects and consider the circle. As I shall discuss later, we can think about the idea of circles extended into the complex number system, and we can also define analogues of circles in other more exotic structures such as networks. Okay, so the rational numbers and the real numbers are models of the continuum. So I think a good question to ask is, what is the real essential nature of a circle when treated as a continuous object? What's its most important defining features? Well, the area of topology gives us a nice way to approach this question, because topology is concerned with the attributes of geometric form which are preserved under deformations. So rather than asking about circles, we can ask about loops. That is, any kind of object you can get by drawing a kind of curve which comes back and meets itself. What are the topological features of those things, and how would you define a loop? I mean, a circle is obviously a kind of loop, and so by understanding the topology of loops we grasp a lot about the circle. So the definition of a loop in algebraic topology is very simple. It's just obtained by taking an interval and then gluing together the two ends of the interval so that it becomes seamless. And so in this way it's an example of a topological manifold. The quintessential one-dimensional manifold would be the real number line. The reason it's a one-dimensional manifold is that if you were a one-dimensional being on that space, then you would see the same kind of neighbourhood, the same kind of immediate surroundings about you, no matter where you are on that space. And the same is not true for an interval with definite endpoints, but if we attach those endpoints to one another, then we do get something which has this manifold property, the loop, and of course the circle is an example of that. So it's interesting to think about the ways that loops appear, and of course they appear in so many places in mathematics. I just thought I would give one interesting example which shows how loops can come about in systems which seem to have nothing at all to do with cycles or curvature. So the example I want to talk about is if you have the real number line and then you have an operation which is add 1 to a number, or if you want to think geometrically, move the point 1 unit to the right. So I've represented how this operation affects different points on the line with these different directed semicircular arcs. And so we can see that the line here is sort of partitioned up into different sets which sort of form orbits, if you like. So for example, we have the red orbit, which consists of all the points you would visit if you start at a particular location and repeatedly apply this operation. You won't visit every point on the line, you'll just visit particular points separated by units distance. Now if you start somewhere else, then you'll visit all the points which are on this black orbit, and again we have this green orbit. And so we can think of an orbit as the set of all points that you get to by applying this move 1 unit to the right operation as many times as you like, or applying the inverse move 1 unit to the left operation as many times as you like. And so essentially, if we now think about all the orbits on the line, it's interesting because we can separate them out. I mean, you can imagine colouring them in with different colours. There would also be a yellow orbit and an orange orbit, and I mean we'd soon run out of colours, but you can try and visualise what I mean. And if you think about it, if we want to understand the set of all these orbits, we can just take a unit interval and we can pick a representative of each orbit. There's just going to be one point in that unit-sized interval on each orbit. So let's say that the leftmost point in the interval was this blue orbit, was this black orbit. So then as we move to the right we find other coloured orbits, and then after we've travelled a unit to the right we'll again be back on the black orbit again. So essentially this space of all orbits is topologically equivalent to a circle, because we can just take an interval and then we can get one of the representatives of each of the orbits, and then if we move slightly out of that interval, we again return back to the first orbit that we considered, just like when you move to the right of this interval with its ends attached, you move back onto the left side of the interval again. Okay, so we've just had a look at what a loop is, as considered as a continuous object. We can also think about such things in a discrete way. In fact, this is a lot closer to our everyday experience of countable discrete objects. And so, a very natural way that cycles and loops arise in this context is in the theory of functions. So a function is something which puts some kinds of objects in one set in correspondence with another set of objects. And it's typical to think of functions in terms of some kind of a operation that changes something. For example, here we're considering the operation of doing a 90-degree rotation, and the object that we're looking at is this smiley face here. So I've used arrows to represent the effect of this 90-degree rotation operation, and you can see here that if we do this operation 4 times, then we get back to where we started from. So this is an example of a so-called period 4 cycle, and it's a directed cycle which is induced by this sort of function here. So it's interesting to see how these cycles emerge this way, because this is very common. Whenever we're going to repeatedly apply some sort of a transformation to something, there's only really 2 possibilities. Either we can keep applying the operation indefinitely and never return to any place we've already visited. For example, if we keep adding 1 to something, then we can just keep doing that forever, and we're never going to get back to where we started from. However, the other possibility is that if we keep applying the operation, eventually we're going to get an object back that we had before. For example, when we're multiplying by -1. And once that happens, the pattern will repeat again and again and again, because it's deterministic. So that's one way we can get the concept of cycles in a discrete way. Another one occurs in network theory, where we can think of undirected cycles just formed by nodes, by a sort of path of links that goes around and comes back to its own starting point. It's an interesting problem in network theory to try and find cycles of different types. Okay, so that's a little bit about the sort of continuous and discrete ways to view loops, the underlying sort of objects under a circle. But now let's try to get back a bit to what's commonly thought of as circles. So a good way to do this is to have a look at how Euclid defined circles in his book The Elements, book 1. So he defines a circle as a plane figure bounded by one curve, and such that all right lines drawn from a certain point within it to the bounding curve are equal. The bounding curve is called the circumference, and the point is its centre. So of course we don't know exactly how Euclid would have defined it, because the Elements has been reworked a lot of times over the years. But it's clear that in Euclid's thought, the important notions of a circle are that lines which are perpendicular to tangents go through the centre, and also this concept that there's an equal distance from the circumference to the centre of the circle from any point on the circumference. So I think that's the real important essence of how we typically define a circle today. This is how I would define a circle. If asked for a quick description, I'd say it was the set of all points in a plane which is a fixed distance away from a given centre point. And so this is a very interesting notion as well, because it allows for quite a lot of generalisation. You see, the distances are obviously defined in two-dimensional and three-dimensional ordinary space, but they can also be defined on many other types of mathematical space. In fact, there's a general concept of what's called a metric space, which is basically just a space with a distance function defined upon it, and generalizations of the circle can be thought of on any of these spaces. And of course there's a lot more spaces out there than just two and three-dimensional ones. We have fractal spaces, spaces of functions, all sorts of things. So it's interesting to consider these generalizations of the concept of a circle. So if we have a particular two-dimensional manifold, that is, a surface, then we can consider a sort of generalized distance function upon that surface. If we think of the surface as embedded in 3D space, as is natural to our experience, then we can obviously define distance in the ordinary way in 3D space. And then if we say get a piece of string of a unit distance, well then we can stretch that string across our surface and push the string into it so that it's tight. And that essentially gives us a sort of definition of distance within that surface. So we'd say that two points are separated by a unit distance when the shortest path between them has a unit length, that path being confined to being within the surface itself. And so then once one has this definition of distance, one just uses it with this idea of a generalized circle. And so one gets the idea of generalized circles in different surfaces. Now, one of the things that's interesting about this is that our standard ideas about circles don't necessarily hold in this case. For example, we have this formula that the circumference of a circle is equal to 2 pi times its radius. Well, if the surface has some kind of curvature to it, then that formula won't necessarily hold true. It's also interesting to see that when we consider other kinds of surfaces, other natural ideas about the circle don't necessarily have to work. For example, we generally have no problem in a plane thinking of the inside of a circle and the outside. But consider the case where we have a torus shape, a sort of donut-shaped surface. There we can draw circles where the question of which is the inside and which is the outside of a circle can be very difficult to answer. It's also interesting to take this idea of these kind of generalized circles and consider them within more exotic types of spaces. For example, networks. This is a fragment of the so-called Kevin Bacon graph. So here the nodes are the actors, and we'll link a pair of actors when they've co-starred in the same film. And so we get this social network of actors, and in networks we can also consider distances. We'd say the distance between a pair of nodes is the number of links that you have to traverse to get from one to the other. And so we can consider a sort of generalized circle centered upon Kevin Bacon, consisting of all the actors who are 2 hops away from him in this sort of film social network. So for example, Ben Kingsley would be within this circle of radius 2 because he's co-starred with John Cleese, who's co-starred with Kevin Bacon himself. Okay, so now let's come sort of full circle, so to speak, and come back to this view of the circle in terms of the settable points at a distance r from the origin. How can we describe this? Well, it turns out that we can use Pythagoras' formula to get a fairly nifty description of this if we also adopt these Cartesian coordinates. So in Cartesian coordinates we describe a point in the plane as being a distance x to the right of the origin and a distance y up from the origin. And so if we apply Pythagoras' formula, which says that the length of the hypotenuse of a right angle triangle is the square of that is equal to the sum of the squares of the other two sides of the right angle triangle, well, we get this nice formula: x squared plus y squared equals r squared, where r is the radius of the circle. So a point which is x across and y up is going to belong to the circle precisely when these conditions are satisfied. So this gives us a really nice, succinct definition of a circle in a plane. And it's very nice because it's extremely clear about what it means, except for that we're not being clear about what number system we're going to use. But that's a good thing, because we can interpret this formula using many different kinds of number systems. Perhaps we're only going to allow x and y to be rational numbers. Maybe they can be any real numbers. Maybe we'll even allow complex numbers. But whatever we do, once we've fixed what r is, allowing x and y to be anything that satisfies this formula defines as a circle. And this is very satisfying. However, it also shows how the circle, being a quadratic kind of object, opens the door to some rather difficult to deal with ideas. I mean, the Pythagoreans followed the teaching of Pythagoras, who of course has his name associated with the famous constant to do with a circle. But the Pythagoreans were deeply troubled with some of the things that can come fairly easily from a formula like this one. In particular, there ought to be a circle like this that can satisfy this type of equation when x and y are both equal to 1. But in that kind of case, what sort of radius would a circle like that have? Well, according to this formula, its radius would be the square root of 2. And the square root of 2 was something that deeply troubled the Pythagoreans. So much so, in fact, that they killed one of their members, Hippasus, for revealing the secret of a particular quality of the square root of 2, and that is that it is irrational. It cannot be written as a fraction. And this really, it's hard to imagine what a big blow this was to the Pythagorean worldview, because as far as they'd seen so far, everything in the world that they'd thought about, that they'd considered mathematically, they reckoned that they could express it as a fraction. And here they found, deeply embedded within this normal geometry, there was numbers that could not even be written as fractions. So this isn't the only place where the circle yields this kind of irrationality. I mean, the constant pi itself is another one of these rational numbers. And this kind of issue of the circle having these difficult to grasp numerical relationships is very much with us today. I mean, the standard way a lot of people think of circles is in terms of these trigonometric formula involving the cosine and sine function. And these are actually extremely complex functions if one looks at what the definition of them is. The most satisfactory way to define cosine and sine is generally in terms of these infinite power series, which are very difficult to really think about in a down-to-earth manner. But anyway, this is still a very, very useful way of looking at the circle. We think about an angle, which as it grows, a particle will move around the circle, and then we can describe the x and y coordinates of this particle in terms of the cosine and sine function. In fact, x being r times cosine of theta, y being r times sine of theta. And so this is very useful because it relates the circle to lots of interesting trigonometric properties of triangles. And it's also extremely nice in the way that it ties together with Euler's formula. So I've done a video before about Euler's formula, but that was Euler's other formula. It turns out that Euler, who was one of the most prolific mathematicians ever, created two formulas which are often amongst top 10 lists when mathematicians vote on the most beautiful formulas in the whole of mathematics. And I want to talk about the other one now, which is something which ties together these trigonometric functions, the circle, imaginary numbers, and calculus, all in one tiny formula. It's very, very beautiful. And here it is. So what this says is that, well, hang on, before I get into what it says, I better give some background. This quantity I here denotes the square root of -1. If you're not familiar with this idea, think about it for a moment. What number can you multiply by itself to get -1? Not -1, that gives 1 when you times it by itself. So it's not an easy question to answer, but if we just imagine that there is such a number, the square root of -1, and we call it I, then it turns out that it makes sense to think of these imaginary numbers as running kind of perpendicular to our ordinary real numbers. So if we have an origin 0, and we imagine our real numbers as counting off to the right, 1, 2, 3, 4, and so on, then it makes sense to think of the imaginary numbers as going perpendicular to that, upwards, I, 2i, 3i, and so on. And in general, a number will have a real and an imaginary component. For example, 2 plus 3i could be visualized as a point 2 units to the right and 3 units above the origin. Okay, so now we know about what I means in this formula, and theta is this angle, and it's basically the same as the angle in the previous picture we're looking at, because we can view the real and imaginary axes like the x and the y axis from before. So theta has the same interpretation. The only other thing in this formula to know about is E, and that's Euler's constant. Its value is approximately 2.718, and it has many applications in calculus. But what this amazing formula says is that if you take this quantity E and you raise it to the power of I times the angle theta, then that's going to be equal to cosine theta plus I sine theta. So what it's essentially saying is that raising E to an imaginary power corresponds to a rotation around this unit circle centered upon the origin. So it gives us a really beautiful description of the unit circle, that it's just, you know, a unit circle visualized in a complex plane is just all the values of E to the I theta, where theta varies from 0 to 2 pi. Really remarkable formula. However, as beautiful as this formula is, it does involve cosine and sine, and so it sort of has this transcendental aspect to it. For example, if one says what's e to the I theta, where theta is 0.489265, well, this is not the kind of question that one can really get exact answer to, rather than except just to restate the question. It's not something that can be evaluated to a fraction or to a kind of canonical form easily. That's not the case, of course, when one's dealing with rational numbers. Rational numbers can always be boiled down to a sort of simplified form. And it turns out that one can deal with the circle in a completely rational way, and there's quite some advantages to doing this. So it's useful to look at this kind of so-called projective definition of a circle. Perhaps I shouldn't call it the projective definition, let's call it the rational parameterization of a circle. So the idea here is that rather than describing the circle in terms of an angle theta, which varies from 0 to 2 pi, as we did in the previous couple of pictures, now we describe it in terms of a number h, which can be any number, positive or negative, and it can even go to infinity. And if you're going to use this kind of number system, you may want to only deal with rational numbers, in which case if you pick h to be a rational number, you always get rational answers. And the basic idea geometrically here is that h is the height above the origin that this line that you're going to draw out from -1, 0 passes through. And then we have this formula for x and y, which give the coordinates, the Cartesian coordinates, of the other point on the circle. And so this is a very nice way to look at the circle as well, because it gives us a completely rational view of the circle. And so by varying h from -infinity to infinity, we're essentially sliding this line around and sweeping out all the points on the circle. It also gives a fairly interesting correspondence between the sort of set of all points on the circle and the set of all points on the line, and we see that there's some kind of similarity in the sense that it's kind of like as we go to infinity on the number line, we sort of pass from the left hand side to the right hand side, and so in some sense there's some similarity between the whole number line and the circle. This is more clear in projective geometry. So I thought I should just mention briefly about conic sections. So these are interesting because they provide another kind of generalization of the circle. A cone can be defined in 3D space as something you get by taking a point and taking a circle that's plane doesn't contain the point, and then the cone is a set of all lines that go through that point and the circle as well. And the thing is about a cone, if you slice a cone with different planes, you get several different kinds of curves called conic sections, and these have a lot of similarities to the circle. So if you slice the cone by a plane which is parallel to its base, then you get actually a circle. If you slice the cone by a plane which is tilted a little bit, you'll get an ellipse, which is associated with the circle, but it's a kind of stretched out circle. And orbits of planets generally follow ellipses. Usually the set of ellipses is considered to contain the circle as well as a special case. Tilting the plane a bit more so that it's parallel to the generators of the cone gets you a parabola. which just sort of opens out, and so the sides go parallel, unlike an ellipse which closes back up. Parabolas are also associated with gravitational bodies in that they give the trajectory of a projectile which is launched. And then tilting the curve further, we get a parabola. We get a hyperbola. Okay, so the reason that I mention conic sections is, well, for one thing, they're a sort of generalisation of a circle, and as such they share many of its properties. But more importantly, conic sections can be defined much more clearly, or much more straightforwardly, than can a circle in projective geometry. So in projective geometry, one doesn't begin with the concepts of distance and so on. And so it's actually difficult to distinguish between these different conic sections. And it turns out that there's a rather elegant way to define all of them, either in terms of projections or in terms of things called polarities, which I haven't touched upon. And having done so, one can then define what a circle is as a special type of conic section. And it's interesting because, in fact, at least one definition which I've seen due to von Staudt, which I think is very elegant, defines a circle in terms of imaginary elements in geometry. So this is the sort of final thing I want to touch upon just very briefly, and that is that the circle, looked at algebraically, can be thought of in the simplest way perhaps by that equation x squared plus y squared equals r squared. And as such it naturally links to the realm of complex numbers. But not only that, it naturally suggests the existence of complex points and complex lines. We can represent a circle of unit radius which is centered upon the origin by a very simple equation: x squared plus y squared equals 1. So 1 here is the radius of the circle, and when x and y satisfy this condition, then the point xy is upon the circle. So it turns out that this is useful for many different applications, of course, but one thing that it does is gives us a way to look at the sort of complex extended structure which we can view a circle as having. Now, this structure isn't immediately obvious to our eyes in fact it gives us a notion of a circle that's much more rich and complicated than our standard concept of it, but it is consistent and it's quite a useful idea. So firstly, if we just draw a line, we can ask, where does the circle meet the line? Well, we might as well pick a line which has a simple equation. So we'll just pick a line which is a height h above the origin. So the line here is specified by the equation that the y coordinate is equal to h, where h is the height of the line above the origin. And then we can find where these two objects meet, this circle and this line, by solving the equations. And this is fairly straightforward. And we find that the solutions are that x equals plus or minus the square root of 1 minus h squared, and y equals h. They are the values of x and y, which give points lying on both the line and the circle. Okay, that's all fairly straightforward, but then what happens if we move this line upwards a bit? Well, algebraically, this doesn't change anything, and that's a very telling fact, because obviously when we look at the next picture, it looks vastly different to us. We would say, hey, there are no common points of this line and this circle perhaps, but the algebra doesn't distinguish between the two cases in the fact that it provides a solution. The only difference now is that the solution is complex. it involves imaginary numbers, the square root of -1. And basically it's the same solution, but we can write it a little bit differently, bringing the square root of -1 quantity outside of the original square root. And we find that x is equal to plus or minus the square root of -1 times the square root of h squared minus 1. So in this case here, where the line's high up, where h is greater than 1, this quantity inside the square roots on the right side, h squared minus 1, all square rooted, that's a real quantity, but it's now multiplied by this imaginary quantity, the square root of -1. So how, if any way, are we to visualize this? Well, the standard idea would just be that these solutions exist, but they're in a kind of extended number space involving complex numbers. And so, do these issues actually come tangential to standard geometry, the type which Euclid would do with a straight edge and a compass? Can we view these things through that? Well, in fact we can. I'm not going to go into a vast amount of detail here, but essentially von Stout developed a theory of how these imaginary quantities, points and lines and such, can be treated in a purely geometric way. And here is a construction which essentially gives us this setup. It gives us this quantity, h squared minus 1. I'm going to describe how to do this setup, but it's more than a simple geometry trick. I mean, this construction here, which I'll describe in a minute, does allow you to get this quantity, h squared minus 1, all square rooted, which is the size of the imaginary part of the meeting points of the line and the circle. So it matches up well with the sort of algebraic theory of the complex contact points of lines and circles, but the correspondence is much deeper than that. This kind of construction can be used, for example, to find where any conic meets any line, and more than that, it matches up with other things such as the theory of elliptic involutions in projective geometry, which can be used to provide a completely geometric representation of complex points and lines in completely general settings. And one can ask things like, what is the line joining two complex points? And answer that question completely geometrically without having to turn to algebra at all. Now, I've done some videos on this subject. I think it's something which ought to be more well known to geometers, but that's not what I'm going to focus on too much today. I'm just going to go through this construction and show how it can be used to give a sort of geometric notion of this extended structure of a circle. Okay, so here I have a circle and a point, and I'm going to get right to making this construction to find the size of the imaginary meeting points of this circle and this line. So we'll do this in a purely geometric way. So let's begin by drawing a line perpendicular to the centre of the circle to meet our black line. So we're interested in finding out where this circle meets this black line, and it will do so at imaginary points, and we're going to make a representation of them. So the next stage is that from this point we've just found, we'll draw tangents to the circle. Now what we're also going to do is to draw some parallels to our original line at the place where this line through the centre goes through the circle. So this gives us two new lines parallel to our black line, and now we have 4 points. And so if we draw in the two missing lines through these 4 points, then we see that those are going to join our original black line at these two new points, and that's what we're looking for. So we have these 2 points to the left and right of our original point on the horizontal line, and if we look at this distance from the centre to, let's say, the right hand side, this will be this quantity, square root of h squared minus 1, where h is the height of the black line above the centre of the circle, if the circle's of a unit radius. And so this is essentially what's called the amplitude of the complex contact points of the line of a circle, also known as the sort of size of the imaginary component of the of one of the contact points. So there's actually going to be two of these complex contact points, plus or minus this amplitude times the square root of minus 1. So I don't want to go into too much detail here, but what I am going to do is just visualize the complex structure of this circle a bit more. So and turn the trace on. Now the thing is that these are just a couple of points, but if we shift this line around, we can see all the different points where the circle makes contact with the line when this line is at different distances from the centre of the circle along this single direction. And so what we see is that when the line is close to the centre of the circle, then there are two contact points, and those are real, these black points of the thing we normally associate with the circle. But when we move this line away, we get these purple points, which are imaginary quantities, and the sort of size of their imaginary components are given by the distance from this black point to the, let's say, the right hand side purple point. So then we see that these quantities are increasing in imaginary size as the line moves away. So essentially, by varying the line in this way, we get a sort of sampling of all of the points from the circle, the imaginary points, well, not all of them, but some of them. Now if we imagine rotating around this diagram so that we look at the lines in different directions and how those sweep out similar kinds of structure, we can start to get an idea of what the kind of complex structure of a circle is like. Now let me just quickly show you a bit of a demonstration to show that this notion does have some teeth, and it's not just a sort of whimsical thing. So let's say we have two circles, and we want to find out where those two circles make contact with each other. Well, if they're, let's say, like this, then it's fairly easy to find a couple of contact points with these circles. And let's make some observations. There's a couple of Euclidean theorems we're going to think about. One is that if we have a couple of circles, then it turns out that if we find a sort of common chord of those two circles, that's always going to be perpendicular to the line through the centres of the two circles. The other idea is that if we have three circles and we draw all the common chords between pairs of them, then it's another Euclidean theorem that those three common chords always meet at a point. Now let's assume that the same results work in this case here, where the circles are far away from each other and they don't have any real points in common? Well, if we assume the same thing works, we can also find a solution in this more general case. So assuming that these two circles do have a common chord, according to our first fact, it ought to be perpendicular to the line through their centres. Now secondly, well, to make use of the second fact, let's draw a third circle in here. Now it should be that the common chord of these the common chords of these circles ought to all collide. So we can draw two of these in. Let me just colour this first line in a different colour to avoid confusion. Now, if these two things do have a common chord, well then it ought to be going through this point here, and it ought to be perpendicular to the purple line. So let's draw it in. I shall make it thicker to distinguish. So using our assumed facts about, assuming that those facts kind of generalise to the complex case, this thick black line ought to be the common chord of these two circles in black. So let's see if that's so. Well, we can do this by using our previous construction to figure out the meeting points of these circles with this line. Let me just erase these construction lines. Okay, so if we've done that all correctly, then these 2 points here and here on this red line ought to give the amplitudes of the meeting points of the left-hand circle with this red line. Now if this red line truly is the common chord of these two circles, then the same should be true if we do the same construction involving the right-hand circle. So let's see. Okay, it looks good. Looks like it's working. Yeah, we get results in complete agreements. So this construction does seem to verify the theory that I've said, at least that it works in this case. Anyway, there's much more to this, but I just wanted to give a sort of very basic flavour of what this complex of structure of a circle looks like. There is a more rigorous way to study it through, for example, Hermitian matrices, and with that one can see that the structure of a circle is a very rich object. One can consider things like circles with imaginary radius, and also one can see things like that a line can be considered to be a special case of a circle, and study that in a very sort of consistent theory which meshes well with things like the theory of Mobius transforms. Another thing about this theory which I've learnt a bit about from a book by Lawrence Edwards called Projective Geometry, which I'd highly recommend. And in that book he discusses how the circle can be viewed as a special kind of conic, and conics can also be treated with this sort of theory of imaginary elements. However, with the circle, it can really be defined as a conic, which goes through this sort of imaginary points at infinity, which is a very interesting notion. So if one looks again at this picture, when the line goes infinitely far away, one sees that the sort of amplitudes of these, or these sizes of the complex meeting points of the line of a circle, become infinite. And in this sense, the circle has these special kinds of meeting points with the line at infinity, at these kind of absolute quantities, and this can really be thought of as a defining feature of the circle.